Nice to see that so many of you show up today to this focus session. I think this is going to be a very, very exciting session. It is my pleasure to introduce the first speaker, Pablo Alonso-González from University of Oviedo, and he will speak about Plasmon and Phonon Polariton mapping in 2D materials. Pablo, it's yours.
So, okay, thanks a lot, Adrian, for the introduction. Also, thank you, Rainer, and the organizers for putting together this super nice school. I actually learn a lot these days. So, yeah, I'm from Oviedo. Oviedo is, for you, those of you that are not from Spain, it's 400 kilometers farther to the west, in the coast. It's a little town. We are there at the university, and we have this quantum nano-optics lab. And one of the research lines is on polaritonics, which is my main expertise, I would say. Today I'm going to talk about how to map them with SNOM, particularly two types of polaritons, surface polaritons. Graphene plasmons and phonon polaritons on MO3. MO3 is a very highly anisotropic material, and then the polaritons have very special properties, such as that the wavefronts are not circular anymore, they are hyperbolic, and this induces really exotic phenomena, like this one that I will show you what it is, and this one. Okay, but let me start answering why studying nano-optics or surface polaritons. You know that the diffraction limit of light imposes that you cannot see below the wavelength of light divided by 2 because of diffraction. So how to do nano-optics if you cannot see, for example, lambda divided by 2 in the visible, 500 nanometers divided by 2, 250. So you cannot look at volumes or sizes below 200 nanometers, then nanotechnology or nanoscience doesn't make much sense, right? So there is one way to circumvent this fundamental limitation, diffraction, and it's the excitation of surface polaritons. And what are surface polaritons? Surface polaritons is just the surface wave at the interface between two different media. This media, the difference between them is the permittivity. One has a positive permittivity, air, for example, and this has a negative permittivity. For example, in the visible, a metal. I will show you that it's not only metals that have a negative permittivity. Metals have negative permittivity in the visible. In the infrared, also polar crystals, they have a negative permittivity. And this allows to have this surface wave. But what are the properties of these surface waves? Well, the main property is that they are a mix between light and matter. So it has the properties of light, like frequency, but then because it involves matter, moving matter, in the material, in metals, free electrons, in these other polar crystals that I say is going to be the lattice, then because it involves mass, the momentum is larger of these waves. Let's see this way. So it's like a heavier wave, it moves mass, and then the momentum is larger. What is the momentum? It's the wave vector, basically, okay? And the wave vector is a vector, so then they say that the norm of the modulus of the wave vector is it's 2 pi divided by lambda, so it says you about the wavelength, the size of this wave, but it's also a vector, so it's momentum, okay? It's parallel to momentum. Okay, so we have this dispersion curve of this wave, and this dispersion curve, this is just omega k, okay? And here I plot you the light line, so this is what you know very well, the slope, phase velocity, and the velocity is the speed of light. But now we have a wave that has a dispersion to the right, to this light the line that is here. Meaning that at the same frequency, I told you that this wave has some properties of light, the same frequency, for example, but now the wave vector is larger, meaning that lambda is smaller. On the other hand, the slope is smaller as well, meaning that the velocity of these waves is smaller in the quantity that the wavelength is shrinking. So we have a trade-off. We are shrinking the wave by the wave of the incident light in this material, making it smaller. You can make nanolight it will propagate a bit slower. But 1/10 of the speed of light is still super fast. So we can do nano-optics, but at the nanoscale, okay? So here we can go to really small values of the lambda. So this is a cool wave that we can work. But on the other hand, this is an evanescence wave. It decays exponentially, so it does not propagate very long. That's the drawback. But still, it leaves some time, and one can play around with it, okay? But the main, let's say, good properties are that the Polariton wavelength is much, much smaller than the incident wavelength. And because of this surface character of the wave, it is really confined to the media, and therefore the field is also enhanced. So the density of the field around this surface is really high, making that the modulus of the field is, compared to the incident one, is quite large. So it's like a, let's say that we can make something like a nano lantern, a nano light there, okay? That is living a short time, not very long time, but is really intense and small. And this has been studied for years, on decades, on metals. Okay? Metal was the first material where this was studied, obviously. Noble metals in particular, because noble metals, they support this surface plasmons in a longer times. Metals have negative permittivity, as I say here, below the plasma frequency, right? You have the plasma that is free electrons that can move, trying to, it's a negative permittivity. It does not permit a field to come in. That's what does mean, negative permittivity. And how is it doing it? Just by moving the carriers, following the electric field, and by moving carriers, these carriers can re-radiate, and they can, let's say, reflect light. So it's like a perfect mirror. It's actually how a mirror works. Okay? You have a metal, which is a mirror, and then these free carriers, they can move and screen out the field that is incoming and come and reflect back the light. Okay? This is, and there is a small absorption, and this small absorption that can happen in a mirror, it can be surface plasma, this wave. Okay, this is the mechanism, the physical mechanism, and it was worked for years in metals, as I said, and particularly by doing cavities. By making small cavities where these surface plasmas are confined and they go back and forth, you can create like Fabry-Perot cavities. And therefore, the fields can be really enhanced at some points. It can be the extremities of antennas, or it can be in the middle of the antennas, like a capacitor. This is a gap antenna. So here, all the fields are super high here, super large here. And therefore, if you put now molecules and the gap is small, then you can have here like a nano lantern that is illuminating this molecule, and you can have sensing capabilities that you wouldn't have without the nano antenna. And this was really a super result at the time, where they could measure single molecule Raman spectroscopy thanks to this. This was called SERS, Surface Enhanced Raman Scattering. Okay, but metals present some problems or drawbacks. Many electrons, the electrons scatter a lot, therefore lifetime of these surface waves, it's in the range of femtoseconds, 10 femtoseconds. Really short times. Lack of electrical control. You have super large density of electrons, and they can screen out whatever field you put in there. You cannot put more carriers. You cannot control, let's say, the conductivity easily, and then this does not allow you to control, for example, the wavelength of the surface wave. Okay, this is some drawbacks. Here I make a summary. This part is about surface plasmons, short lifetimes. On the other hand, broad spectral range. Yeah? You can have plasmons in a really broad spectral range below the plasma frequency. And here I'm going to present you some other surface polaritons that are a result of the same physics than it was shown before, resulting of Maxwell equations. These are all Maxwell equations. It's also a surface wave. But in this case, the material that has the negative permittivity is not because of free electrons like a metal, it's because it's a polar material, meaning that it's a, let's say, a lattice containing two atoms, very different atoms with very different electronegative value, and therefore the carriers are closer to one of the atoms than the other, and then it creates a tiny dipole between them. And this tiny dipole between them can react to the incident field, screening it out again. So creating a negative permittivity at the same time, and therefore fulfilling the conditions to support these surface waves. These are basically lattice movements. It's not free electrons. Here, the electrons are bound to the atoms. Okay, it's the lattice that is moving, and these are the phonons. Okay, the phonons of the lattice. So we incident light, and the lattice starts to react to this incident light, and it can screen out the field, and again, it's like a mirror. So in the infrared range, this occurs in the infrared range. Okay, in the infrared range, these are the mirrors. These polar crystals are dielectrics. In the visible, they are dielectrics. They are not reflecting at all, but in the infrared, they are really good mirrors. Okay, okay, what are their properties? They normally, the most, let's say, studied ones, these materials are, they started with silicon carbide. I remember Professor Greffet and then Fritz and Reiner were measuring also silicon carbide at the time, here, 2002, measuring with SNOM, exactly these resonances here, okay? Then later on, like 13 years later, there was again a lot of work on Phonon Polaritons. I think it was Josh Cadwell working with also silicon carbide and other groups that, yeah, the technique also was developed, and then many other systems were worldwide, and people started to work again on these materials. Recently, very recently, 2021 and 2022, two other bulky polar crystals were studied, calcite and BgO, gallium oxide, because they support phonon polaritons with kind of strange properties, highly anisotropic. And here, these ones are called ghost polaritons. These are called shear polaritons, if you want to check it in the reference. I'm not going to talk about this, okay? But just to make you know that there are other, let's say, exotic excitations on these crystals. Okay, but what are the properties? Okay, it's negative. The permittivity is negative. This movement of the lattice occurs between the TO phonon and LO phonon. This is a much narrower spectral range than with plasmons. Okay? This is one of the drawbacks of phonon polaritons. And this is intrinsic to the crystal structure. So it cannot be tuned easily. On the other hand, as it involves phonons, scattering occurs in time scales much longer than electron-electron scattering. Therefore, long light times, okay, in the picosecond range. And therefore, you can make optics, nano-optics. You have more time to do it. And if you make cavities, they can go back and forth in the cavity much more times, and then the quality factor can be larger, and then you can make, for example, nanocavities that are much better for sensing, for example. But everything occurs in the infrared, okay? 10 microns, 7 microns, 11 microns, 12 microns, okay. On the other hand, these polar crystals are typically very difficult to engineer. They are quite tough materials. Well, we are trying to improve these things, and it has improved somehow during the years, but still it's quite difficult. Okay, these are the things, and then suddenly these van der Waals kick in, right? This is a very nice image from a paper from Dimitri, I like a lot, where here they show all the light-matter interactions that happen in these van der Waals materials. These are van der Waals materials because they are layers, right, okay, that are connected by van der Waals forces in the vertical directions, weak forces, and covalent bonding in the plane. So they are really sheets that are really well connected, let's say, chemically in the plane, but out of plane they are not really strongly bounded, and then you can just pick it up one layer, two layers, etc. Okay? You know, graphene and others. The thing is that in these layers, there can be a lot of matter excitations, depending on the layer that you are studying. So there can be free electrons. So you have surface plasmons, as I saw before, then plasmon polaritons, and this can be graphene, for example, because it's a semi-metal, or black phosphorus, which is a semiconductor that can have many carriers, free carriers, and then they can support plasmon polaritons. But also you can have materials that have these lattice vibrations, these phonons, and then you have these phonon polaritons, and for example, the first one that was studied, again in the group of Dimitri, hexagonal boron nitride phonon polaritons. Okay? And then there are others that are topological insulators. And here I will show you that there are others that are quite kind of strange. Because of this van der Waals stacking, the materials are highly anisotropic per se. And this is giving really exotic properties of the phonon polaritons. OK, there are other excitations that I'm not going to talk, but some of you work on that. Exciton polaritons, transition metal decalcohenides, they have these excitons, and these excitons can couple to light. They can travel. They are not strongly confined, but they are very interesting. They can give you a lot of information about the physics behind the semiconductor. And then there are these other two, copper pair polaritons and Plasmon polaritons that, as far as I know, they have not been visualized with SNOM, and the physics might be super interesting, okay? And for this, I think that you need a low temperature cryo-SNOM, and for Plasmon polaritons, I don't know. I still many 2D materials that are appearing, and maybe very interesting topics that one can study in the future with this magnificent tool that is SNOM, right? Okay, so here I put this link. It's for Dimitri's webpage that I like a lot, this Polariton panorama. He made the effort to find all polaritons, not surface polaritons, or polaritons in the different topics, putting all together then and making updates of them. And then you see that there are many of them, okay? There are hundreds probably of polaritons in physics study. They are all about light and other excitations, light matter is coupling pseudo-particles, okay? Very interesting. Okay, but let's restrict this to these two, okay? Plasmon polaritons and phonon polaritons. Therefore, here I put some references. If I didn't put one of your references or whatever, please don't be pissed with me. I'm just putting some that I know, and then I know well, and I want to explain some of it. First of all, it's about graphene plasmons. What are graphene plasmons? I explained you that they are surface plasmons, but why graphene plasmons are interesting? And this was particularly triggered by Frank, that is here, where he proposed theoretically in a paper very nice properties of graphene plasmons. Also in the group of Dimitri, they were mentioned by nano-FTIR and so on. And the main key property of graphene plasmons is that you can tune. As I told you before, surface plasmons you cannot tune spectrally because you cannot put more carriers and then change the properties of the media easily, for example, with electric field. But in graphene, you can do it because it's semi-metal, and then by just making backgating, putting a voltage below, you can put more carriers or less carriers. And by this, you are like changing, let's say, the density of the medium, and by changing the density of the medium, changing the properties of the wave that is propagating in the medium. It's like having a wave in the ocean, and then you're changing the content of salt or something, the density of the medium, and then you can change the properties of the wave. This is unique for graphene plasmons, okay? Therefore, this you can change with the voltage, and this is the Fermi energy, what you can change, okay, with the voltage. The other property is that just one atom thick. And this means that it's such a small, let's say, thin layer that the polariton is really confined to this surface. It's reality a surface, okay? And therefore, the wavelength of these surface polaritons is really, really small compared to the incident wavelength. So you can really go to the nanoscale, okay? So this I put here. And also, it's very sensitive to environment. Of course, it's just the surface, okay? And then, of course, very relevant applications were proposed, sensing and others, okay? I will not talk about applications here, but just how we map them, okay, visualize them. Okay, they were there, they have these properties, but, okay, their dispersion lies to the right of the light line because they have a very large momentum, they are really shrink in wavelength. But at the same time, this strong or large momentum precludes an easy excitation of them. Because for exciting a wave, you need to match the momentum of the wave, right? You want to push a swim, you need enough momentum to make it oscillate. And light, free space light, has no enough momentum. It doesn't cross these dispersions here. For years, in metals, this was solved by making auto configuration. Maybe it sounds to you. And all these configurations where you can get more momentum by exciting evanescence waves and so on. This was kind of complicated here. So one proposal was, it's in these papers, to use a tiny dipole close to the surface of the graphene. And this tiny dipole in the near field, it can have many case values, many momenta, a lot of momenta, that can maybe excite in the near field the surface plasmon. And immediately we thought about this norm, because it's in reality the tip is a tiny dipole, okay, at the apex, as we saw these days where they explain when we illuminate and so on. And actually Rainer showed this in one of his slides, right? It's a numerical calculation where you can see that the lining rod effect there, it creates a lot of carriers here at the extremity, and this creates a huge field. And this field, if it's very localized in space, and you take, for example, the Fourier transform, this is a mathematical explanation, it's just the inverse, right, in the space. So if you have something that is really localized, and you make the inverse, you have something that is broad, and you go to the K moment, to the momentum to K. So basically, when you squeeze in a very small volume fields, you are creating something that has a lot of momenta around. Therefore, we thought, okay, this maybe is enough momentum to launch these surface waves that are so confined. And the experiment was really easy. I think the first day we saw graphene plasma, just put in the sample there, the right sample that Frank brought to the lab, I remember, I think. It was graphene on silicon carbide. And then we measured with SNOM in Rainer's lab, and we saw this, fringes. And this is what we are already used to it, fringes everywhere. Okay, but in the beginning we didn't understand very well how was the mechanism of the SNOM to produce these fringes. We were sure that these are plasmons, but what was the mechanism producing them, okay? And I can tell you now that this is what is called plasmon interferometry. So the tip is acting as an interferometer. It's like an echo detector. It's launching the waves. It's able to launch the waves propagate, they go to some boundary, they reflect back, and by reflecting back, they interfere with the outgoing wave from the tip, and then this is the reflected back, and there is a reflection between all of them. It comes back to the tip, the reflected one, and goes to the detector in the far field. The tip is kind of a Green's function for the theorists, that is propagating the fields to the far field. So you have these two waves that are interfering, and this standing wave that is formed has normally a wavelength that is lambda divided by 2. And this is what was fitting with the dispersion. So we had an interferogram there, interferometric image, and we could see that this is, it's like a radar for launching and detecting. It's doing both things. Okay, this is the mechanism of polariton imaging, the main mechanism. And this was published at the same time for another paper in Dimitri's lab, but basically the same thing. And this is the tip, how it launches it. They go to the edge, they come back, and then they form this standing wave pattern that are the fringes that we see. Okay, then we study encapsulated graphene, because the lifetime was not really good. So if you encapsulate in HBM, then the mobility is larger, and then maybe we see more fringes. And actually, we saw all these fringes, which for graphene plasmons were, at the time, a lot of fringes. And then we saw that they are here, and this is because this is more technical, and I'm telling this. You see here like doublets, right? Here is a doublet, and here is another doublet, another doublet. It's like a wave that is propagating like this, and it has doublets inside. It's like an envelope, and then inside the envelope there are two peaks. And if you take the profile here, you can see it's much better, okay? You have here 2, 2, 2, 2. I'm saying, oh, why is that? Okay. Well, we realized that we have two contributions. We have the contribution from the tip, so the tip is launching, the polaritons go to the edge, then they come back, so you have the interferometry thing, and then you have lambda half. But at the same time, the edge, here is an edge. The edge is also able to launch polaritons, because when you illuminate it, it, let's say, breaks the symmetry somehow, and then you can have very localized fields at the edge, and they can have enough momentum to launch the wave. And then this edge is also launching polaritons in this way, which are reaching the tip, and the tip is measuring them and sending it to the far field detector. So we have two contributions, but these ones have not lambda half periodicity. They have lambda, is the wave itself, and it's more or less a plane wave. okay? Because it's launched, you can think it of a Huygens principle, at any point, this is launching cylindrical waves, but in the end, because of interference, you create a plane wave that is propagating from the edge down. Yes?
On the previous case, you also have an edge, but why don't you have a doublet there?
Yeah, that's a very good question. In graphene, if you don't have the other one is encapsulated, you have HBM, and I have a clear edge, let's say large edge, that it can create, let's say, better confinement of the field in the graphene in the middle. In this case, it was just the graphene, and the edge is really very. Yeah, it's like a very just one atom thick, and then it's not really enough for launching the polariton. Okay, it's not a good edge, let's say, in just if it's a flake of graphene. I never saw edge launch graphene plasmas just with a freestanding or just a layer that is on top of silicon dioxide. But if you put, for example, a piece of gold on top, and the gold has a clear edge, it's like a contact, and then this edge is able to have this localized field, and then you can launch nicely the polaritons, and then you can see these lambda periodicity fringes. So, yeah, so we have these two contributions, and we try, okay, let's study them. But then you need to feed them with two functions, okay? They are evanescence waves, as I said. Here they have the momentum, which is a complex momentum of the wave, real and imaginary part, and then we have two contributions. One is created by the cylindrical waves that are launched by the tip, that they are cylindrical, they decay like 1 over the square root of the distance, because they are forming cylindrical surfaces, and because of energy conservation, this goes like the square root of the distance. And this other is probably a plane wave. Here, we didn't assume anything. We put there an exponent, a, but it is 1 most of the time. So it's 1 over x, like a plane wave should be. This is the geometrical spreading, okay? How the energy is spreading when the wave is propagating in distance. Okay, so we had these two contributions, and then we fit it, and here you can see how it fits nicely, the doublets. And from here, one can extract the real part of Q, of the wave vector, and the imaginary part. With the imaginary part, you can extract the propagation length, and with the other, you can extract the wavelength, and with the wavelength, you can extract the dispersion, and with the dispersion, for example, you can extract the group velocity, which is the slope of the dispersion. With all together, you can give numbers, and one number that is used in the community is this one, which is a kind of a quality factor of, let's say, propagation properties, and this means this is basically propagation length divided by the wavelength. So how many wavelengths the graphene plasmon is propagating? 25, 20. It depends on, some people say the field, others they check for the intensity. There's a lot of things in the papers. But how many wavelengths it's propagating, okay, more or less. So for propagating applications, this is interesting. This is a good figure of merit, dimensionless. For other properties, I like this more in our works because, I don't know, for me it's more intuitive for cavities and so on, is the lifetime. So how much time is the wave traveling? And this you can do by dividing basically the propagating length, which is extracted here from this decay, divided by the group velocity. And this, we saw that is 500 femtoseconds for this graphene. Remember, I say in plasmons, in metals, it was 10 femtoseconds. Now we have 500 femtoseconds. Okay, it was quite enough an improvement. Okay, nice. They can be tuned. They are much more long-lived. They are in a surface where you can put things and maybe sense them. And this created like a topic in polaritonics. Okay, and then there were many, many works. But here I finish on just seeing graphene plasmas on flakes, on sheets. So we can say that the baby is very happy because we can visualize surface plasmas in graphene using SNOM. But now the question is, can we visualize nano-optical phenomena such as focusing, lensing, or refraction in graphene with plasmons? So not only making this echo detector interferometry measurement, where you see that there are fringes and then you can see that there are plasmons, but see the wavefronts, how they propagate. So making a snapshot of the propagation. This is different. Okay? And making the snapshot, you can see focusing, you can see lensing, you can see all that stuff. Okay? And yeah, but then this is a problem. Okay? Using the metal tip, that is acting as an interferometer is a problem to visualize these things, to visualize the wavefront. So then we came with the idea in the group of some other groups. I remember in Germany there was another group, and then Martin was talking about this one of these days. In the group, it was being developed dielectric mapping with SNOM. So using a dielectric tip, a silicon tip, where the tip is not really launching, it's just seeing, it's just probing. It's an inert, let's say, it's not an inert. It's a huge thing that is close to the fields, but let's make an approach. And then we think that it's just a mirror that we put close in the near field to pick up the fields that are propagating there. Okay, silicon tip. So then we tried the silicon tip with gold antennas, okay, where we have surface plasmas going back and forth in these metal things. And we prove that you can measure nicely the fields that are emanating from this dipolar antenna with the silicon tip. You just need to come with light, S-polarized light, so you drive here dipolar mode, it radiates, you bring the tip, and then if you measure the Z component of the field or X component of the field, you will see different things. And how do you do this? Putting a polarizer in front of your detector, SNOM detector. And this polarizer can be like this to measure the X component of the field, or vertical if you want to measure the Z component of the field. And the Z component is very different to the S component of the field, okay? Because here you can see that if you measure the Z component, it's quite large here because you have more lines, field lines, more intensity, more intense in the extremities. But here you have a minus and here you have a plus. So here the lines are coming in, here are coming out. Therefore, the phase is 180 degrees. So you have the plus minus, like the typical charge, plus minus dipole. And therefore, you have seen this blue-red very clearly with SNOM in the phase and intensity. If you measure the X component, and this is what I put here because it's more exotic, here you have field entering and coming out, but the phase is the same. Okay? And this is what we measured, this is what it was simulated, and here the phase and the phase, blue-blue, is the same. So we could measure also the X component. So we can reconstruct, let's say, the field. Okay, this is not the whole story. If the antenna is really, let's say, a very good antenna, is launching a lot, then the tip is somehow mixing the components, okay? But this is another story. But for really normal resonators, you can see the fields nicely with the silicon tip. Okay. So then we said, okay, let's see if we can see wavefronts in graphene. But we need to launch them, and the tip is not launching them. So let's put the tip on the surface. And then we create this antenna, just make a piece of gold on top of the antenna, on top of the graphene, and then we illuminate it from far field. It creates a dipole, and like there was a tip here, the field is very enhanced, and it's able to launch these high momentum waves in the graphene. And then let's see if we can put this silicon tip there and measure it. And this was a simulation, okay? The gold antenna was trying to, it was producing these surface waves, these graphene plasmons, and then we put the silicon tip to see them. Okay, but silicon tip is not only dielectric, it's that the scattering, I mean, it's dielectric, the scattering cross-section for the fields, for the elastic scattering of the fields, is much, much smaller than the metal one. Therefore, we are working here with really, really weak signals, okay? The signal-to-noise ratio was really low in the beginning, but we were improving it and so on, and we got this. So we did the antennas, and actually, we saw the fringes coming out from the antenna. We were very happy to see them. And actually, if you don't have a resonant antenna, this is just a piece of gold. You don't see them much well, because you need a resonant antenna that is launching them, okay? And then we saw these fringes. But look, there is a very interesting thing about these fringes. They are so small compared to the incident wavelength, because it's just a layer of graphene, of carbon atoms, that it's so small that this wavelength of the graphene plasma is much smaller than the antenna itself. And therefore, this creates one thing, is that the wavefront that is produced in these launched graphene plasmas is following the contour of the antenna. So if you shape the antenna, you shape the wavefront of the graphene plasma. And it's only because this wavelength of the graphene plasma is much smaller than the source. This does not happen very often. Our antennas in the roofs are more or less, they are all based on diffraction. So you can create lobes, like the Jack-Wood antenna and all antennas, you get lobes that you can radiate or receive in certain directions. But here, diffraction is at a scale that is much smaller than the antenna. And then, in the end, it's like having the contour of the antenna. So if I shape the antenna, I shape the wavefront. Therefore, we decided, OK, let's make a concave ending. Maybe we can make focusing if it's launching like this. And actually, we saw that you can create a focus. OK, and then you can focus light there in a tiny spot. Not so tiny, OK? Here, for measuring it, it was in the infrared. And we are lambda divided by 30 or so, but it's not really 1 nanometer, 2 nanometers, OK? There are 100 nanometers because we wanted to see it with the SNOM and see the proof of concept of the thing, OK? OK, but we can only not only see focusing. We thought, OK, can we do refraction? Can we make a prism, a lens? For this, we need a prism. We need another element with a different, for example, refractive index, and see the wave passing through, and let's see if there is refraction. And then we thought, OK, maybe we have some areas in the graphene sheet where there are 2 layers. 2 layers, they have more conductivity. And we found one that had the shape of a lens, and this is the luck of the postdoc at that time, the luck I had. And then by having this one, we put an antenna close to it, and then we measure how this was launching the surface waves, and here you can see how they are not parallel to the edge, but they are at a certain angle. And if you evaluate these angles and so on, you see that the Snell's law is fulfilled for these waves. And it's probably the thinnest prism ever demonstrated, right? It's just 1 atom thick. OK, this was super nice, and it was only visible because we use SNOM and a silicon tip. And from that time to now, I think the silicon tip was not really used anymore very, very often. And I want to drive your attention to this, because sometimes the metal tip, because it's launching also waves, is distorting a lot the pattern. And sometimes it's exciting many modes in the field, and they are all interfering. And the modes patterns are really complicated. And if you just put the silicon tip, you are more like looking at the real snapshot of the propagating wave. Okay? But 1 order of magnitude less intense signals. Okay? Normally. Okay. So with this, I go to the next thing. I don't know how much time do I have left. 20. Okay. 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 Then I will skip this part. So I move to molybdenum trioxide Phonon Polaritons. Why these are? Okay, we were talking about surface plasma, graphene plasmon, surface waves, another surface waves, but in a kind of surface wave, they propagate in volume, but it's a solution of a surface polariton. And these are in dielectric, in polar crystals, okay? And one of them that we found is molybdenum trioxide. It's a semiconductor, but it's kind of dielectric. The one gap is quite large. But what is interesting about this material? It is easily exfoliable. You can buy it in the crystals from one of these chemistry big companies. Then we took it, and then we did what many groups in the world were doing, like the tape thing and trying to get flakes. And then we got these flakes, which are very elongated in one direction. And this is because this crystal structure of this material is super anisotropic. So you can see here, it's kind of a complicated. It's a perovskite-like crystal structure. And you can see here that the constants, I mean the lattice constants along the 3 directions of space are very different, okay? 1.4, 0.39, 0.36. So the crystal structure is kind of anisotropic. And this makes that the optical properties are kind of anisotropic, okay? Meaning that if you measure, for example, reflection from these crystals, if you illuminate with a polarization that is along one of the directions, you can get, for example, something where it is not reflecting, but if you go to another direction, it's really reflecting. This means that the crystal along some directions is a mirror, but along others, it's not a mirror. So it's metallic along some direction, but it's dielectric along the other direction. In the plane, okay? Polarization in the plane. This was interesting. So we were thinking, can we measure here? Because these are mirrors. Probably they have, if it's a mirror in the infrared, maybe it's because they have phonons that are screening out the fields, and maybe we can see phonon polaritons. And if it's super anisotropic, maybe these phonon polaritons are crazily strange. And that is fun. So what we did was to measure them with SNOM. Again, it was an easy experiment, I have to say. Yeah? We put in the flake, and then we saw really things like this. At some frequency, not much anisotropy. Okay, well, it's okay. I mean, they propagate alone. This is interesting. Long-lived polaritons. But then at another frequency, we saw this. Only polaritons in one direction in the plane. This is cool. Why there are no polaritons in this direction? And then we started, okay, we need to probe these polaritons with snow along all directions. And how do we do this? Okay, let's fabricate a disk. We have our sonar, our radar, so we can have the tip around, and then we can see reflection along all directions if we make a circle. And this is what we did here by focused ion beam, and we put the tip. This is in one of the restaurant bands, when the material has a negative permittivity, and then we saw that it's kind of isotropic. It's not really isotropic. It's elliptical, okay, in the end. But in the other case, it was like in the other restaurant band, where I saw only fringes in one direction, we saw this. It's like almond shape. This is strange. But in reality, how are polaritons propagating this crystal? How can we visualize this in, let's say, in a better way? You can just take the Fourier transform of the real space image. And then you go to the K space. And the K space, if you, at the fixed frequency, you go to the K space, this is what is called the isofrequency curve. It basically tells you what wave vectors are allowed in this medium to propagate and what are their size, right, their norm. So it tells you a lot of information. And this is a very cool way to represent or to study the propagation of these waves in a medium. And then here we saw that this is indeed elliptical, and we see two ellipses. You see that there are two ellipses? One is because some fringes were generated by the tip, and the other is for the edge. And then we have tip and edge launched. And because the one has lambda half and the other lambda, as I saw before, then you have two radii of the ellipses. Okay? Cool, everything is fitting. And now here we take the Fourier transform, and what we see is a hyperbola. Because we have clear K's here, these ones, then this wavelength is increasing here, so the K, is decreasing here, so K is getting larger, to pi divided by lambda, remember? And at some point there are no fringes, so here there are not allowed K's. And this is what the hyperbola tells you about this material. So it was an in-plane hyperbolic phonon polaritons. And why are they cool, apart of this exotic thing? Because here at the asymptotes, you have infinite number of Ks. And this creates what is called a ray. Okay, you have a ray with infinite number of Ks. The density of optical states along these directions is super high. Another key property is that, I will show you later, the Poynting vector, by definition, is normal to the isofrequency curve, okay? Therefore, if you have a circle, like, for example, cylindrical waves or some isotropic medium, you have plane waves because you have the wave vector, which is collinear with the Poynting vector. Because the Poynting vector is normal to this curve, you have here the wave vector here, and then you have the Poynting vector, they are collinear. Meaning that the wave vector is just the vector normal to the surfaces of equal phase, right, the wavefronts. And if you have a plane wave, the plane wave is coming to you like this, the wave vector is normal, and the energy that you are receiving, the Poynting vector, is also in the same direction. But now, here, if you go here, the K goes to here, but the Poynting vector points out like this. Meaning that if you have a K like this, you have wavefronts, let's say like this, that so light is propagated in this direction, Poynting vector, but the wavefronts are tilted, because K and Poynting vector are not collinear. This is nice. I like it. So, and now remember, reflection, refraction, all these nano-optical things can be explained, or they are induced by momentum conservation. And momentum is K. So what is defining reflection or refraction is the K vector, wave vector, but not the Poynting vector. So the energy can go some way, some direction, that is not the one that we are used to see by momentum conservation. And this gives rise to something that I will show you now, which is negative reflection, negative refraction, and all this stuff. Okay, I will skip this because otherwise I cannot explain the negative reflection. But you can get the dispersion and how we measure, for example, here the lifetime and so on. We took the dispersion. From the dispersion, you can take fitting the dispersion. You can take the derivatives. You can get the derivative of the dispersion is the group velocity. With the group velocity, the propagation length by fitting the profiles, you can get the lifetime. Okay. And when we did this with these Phonon Polaritons, the lifetime was really, really long, 8 picoseconds. It was a record high at the time. But still, you don't see many fringes. Did you see that there are not many fringes, but the lifetime is very long? So the gamma minus 1, which is how many fringes, how many wavelengths is propagating, it's not very many. But it's propagating very slowly. The growth velocity is really slow. So it's propagating in a slow way, long time. But for cavities, this is OK. You can put a very tiny cavity, and it goes back and forth many times, because the lifetime is long. So depending on the application, and this is the key point, lifetime is good, or depending on other is gamma minus 1. I mean, the quality factor, how many wavelengths. You want to make an interferometer, you want to make something optical, an optical device where you want to move this wave here from a very long distance, you need a high quality factor. But if you want to make cavities or light matter interactions with sensing and so on, lifetime matters more. Okay? Okay, this is a thing because I think sometimes in the community it's mixed. People think that by talking about this, the gamma minus 1 is enough. Others, we don't talk much about gamma minus 1. So one needs to OK, Rainer showed this, that if you plot in a polar plot, I mean in the complex plane, in the imaginary part and real part, you can see the phase of the wave if you create a spiral that is clockwise or anti-clockwise. OK, I will not go to here. But OK, the baby is, again, very happy because we can visualize surface phonon polaritons in a strongly anisotropic media with SNON. But again, can we visualize nano-optical phenomena in this media, reflection and so on? OK, but this is what I was telling now. K-vector, Poynting vector is strange. So nano-optical phenomena, reflection and so on is going to be strange. So now let me take you during 10 minutes to the high school or physics faculty for a moment, so to explain very basic stuff, okay? A specular reflection. You have a mirror, you have some wave that comes with a Poynting vector like this, the energy, maybe plane wave like this with this K, and then this is the typical specular reflection, where you put a mirror. Okay. You can see this specular reflection as a momentum conservation principle, okay? How do we do this? Using the isofrequency curves that I showed you before. If it's an isotropic medium, the isofrequency curve is a circle, as I said. You can have propagation in all directions, it's a circle, and the Poynting vector is perpendicular to the isofrequency curve, so we have collinear K and with S, with a Poynting vector, with energy. Okay, how do we do here momentum conservation? We need to put the boundary, because the momentum conservation has to be at the mirror, I mean at the boundary, okay? This is the condition, at the interface where the wave comes. So here we have the boundary, we have this wave, which is this Poynting vector, and this is this K, okay? Collinear, normal stuff. So now we need to conserve the projection of this K to the boundary. So this quantity needs to be conserved under the reflection phenomenon. Okay, so what wave vector in this circle fulfills this condition? So it has a projection that is equal to this one. It's basically this one, the only one that has the same projection. And if you take now the normal, you have there the Poynting vector. So this is the specular reflection explained like momentum conservation at the boundary. Okay, super simple. What happens if I have now this crazy hyperbolic medium? I have, let's take the easiest incoming beam, which is Poynting vector here, and K is collinear. But now, instead of having a circle, I have a hyperbola, isofrequency curve. So now I have here the projection to the boundary, same boundary of this K. This is the same projection here. Which wave vector is fulfilling this condition now? It is this one. But now, where is the Poynting vector? There. It's normal to the curve by definition. So therefore, you have this condition. And this is negative reflection. Namely, that the reflected wave polariton is on the same side to the normal to the mirror. This is what I call negative reflection, okay? So basically, this is kind of weird stuff, but it's all momentum conservation from high school. So then we thought, okay, can we visualize this with SNON, with nanolight, with Phonon Polaritons, because we have a hyperbolic medium supporting these waves. Okay, but we measure these waves with a metal tip. And the metal tip is not able to take a photo, a snapshot of this thing, because it's launching and it's measuring at the same time. So it's measuring back reflection. It is measuring what is back reflected to it. It's not here launching and it's here measuring. It's here launching and it's here measuring. Maybe we can use the silicon tip. Difficult. Let's think a bit more. So then we thought, okay, what if we measure back reflection? How is the condition for back reflection in this media? Therefore, this is the typical back reflection condition. It was normal to the mirror, and it has to come back normal. This is the only case where this is the projection, which is nothing, just a dot. And then the other K on the other side is this one, and then they are one pointing in one direction and the other in the other. This is back reflection, okay? How is this condition in hyperbolic medium? Here, I have these two Ks, and that have the same projection there. So the pointing vector here is like this, and this is like this. So here I have also something that is coming back in the same direction, but it's not happening at the normal condition of the boundary, but at some angle. So this means that here, when I don't know if I saw myself in the mirror this morning, I was so sleepy, but if you look at yourself in the mirror in the morning, the condition is this one, right, where you see yourself. But if we will be in a room in a hotel, it's a hyperbolic hotel, then I will have to put the mirror like this, okay? I have to put the mirror like this to see myself. So tilted. It's really strange, eh? Therefore, we decided, okay, let's try to measure this. Can we measure this? Then we thought, okay, let's try it. So we tried first with HBM. We did the mirror by just milling away some part. And here you can see that everything is normal, the normal hotel. But now, let's see if we go to this hyperbolic medium. Okay, now we have to see this kind of strange behavior. And this is what we did. This is the mirror in MO3, and then we put the tip. And the only position where the tip was getting back reflected waves, it was along this direction, where then it went. So this is the back reflected waves negatively from a mirror. Okay, visualized in the near field at the nanoscale. I never saw a visualization of negative reflection in any other medium or whatever. Okay, and this is the simulation of a tip in one position, and you can see how this happens. Okay, now we thought, okay, we understand now how it's back reflection, but in reality, in this hyperbolic medium, we have not only that K that has a back reflected being, but we have many Ks, right? We have in the hyperbola a lot of Ks. Is there any surface that fulfills the condition such that all Ks come back to the same position? This happens in an isotropic wall. It happens for a circle. In a circle, you just launch a cylindrical wave, and if you make it like a cavity, all of them come back to the same position. You have a cavity, a breathing mode. You remember the breathing modes? And they come back. How is this contour for the hyperbolic wall? Where you launch many Ks in the hyperbola, they all have different pointing vectors, and now you put the surface there, some boundary, and everything comes back. This will be a retro-reflector, something that everything comes back on the same direction. Okay, what is the condition? It's super easy to make the analytical derivation. It's based on the fulfilling that the phase at this point needs to be the same for all the directions, and it's a hyperbola in reality. We made this is the shape of the hyperbola, and if you put here a dipole, you can see that all, while here is going there and here is reflecting at some direction, if you put this shape, everything is coming back. So when an isotropic wall is a circle, here is the complete different curvature, a hyperbola, and then things that are coming here because of negative reflection comes back here like this, and then you have this. And how is a cavity then in a hyperbolic wall? Like this. Okay, it's a cavity with these shapes. So if one wants to make a Fabry-Perot cavity in this hyperbolic wall, and there were papers showing cavities in MO3 doing normal stuff like rectangles, you cannot make a rectangle because the reflection is going in another direction. It's not going back and forth in the same direction. The only cavity that you can make here is making these mirrors. And then you have really back reflection and going back and forth. OK. Then I finish with this strange stuff. If I have, do I have 5 minutes? OK, perfect. Then I move to something that you might know much more than me, Frank for sure, and Dimitri as well, which is this crazy twistronics stuff, okay? When they put 2 layers of graphene and rotate them to the critical angle, and then suddenly the bands, the electronic bands get flat, and because of these flat bands, suddenly the material is a high TC superconductor at 10 millikelvin. Or 2 Kelvin, okay, 2 Kelvin. Okay, this is a super nice concept. It's only 2 layers of carbon atoms, twist one to the other, and suddenly the most crazy phenomenon in solid-state physics emerges, right? And it can be maybe simulated easier than in high-TC superconductors, so a huge fuss about this. Okay, we were thinking, what happens if we take 2 layers, 2 slabs of the MO3 and we twist one to the other? Like this. Do we see also strange stuff in the optical realm? And, and to visualize this, we didn't use the metal tip and getting back the waves by interferometry, because we wanted to see if the wavefronts were evolving strangely or whatever. So then we put, again, the antenna on the top. But because the signal to noise was not very good, we still use a gold antenna. But this launcher dominates because it's a resonant antenna. So it's launching a lot. This is probing. It could launch. But because the reflection is so strange, this thing does not fulfill back reflection. So therefore, we can forget about what is launching the tip. And then we can visualize. And actually, this is a visualization that matches perfectly the simulation of a hyperbolic launch by a point dipole, OK? We are really taking a photo here of what is propagating. OK, so then we did the twisted stuff much easier than with graphene plasmons, with graphene layers. Thick layers, like 30, 45, 50 nanometers thick, and then angles 30 degrees, 45 degrees. Well, kind of, well, I don't want to say easy, right, Aitana, because people working on this with polymers and so on is kind of difficult as well. But it's not like, let's say, critical angle in graphene and so on. OK, we did this. We fabricated the antenna, and we saw this with 30 degrees. Hyperbolic wavefronts. Well, the same, more or less, than in a single layer. Actually, we take the isofrequency curve. We have a hyperbola. It's slightly tilted. OK, we change something, but not much. OK, but it's hyperbolic propagation. OK, now let's rotate them 90 degrees. And by rotating 90 degrees and putting the antenna, we see that now the polaritons propagate in all directions. If we took the isofrequency curve, now it's like a circle. So we recover an isotropic medium. OK, this is nice. So we can go from hyperbolic medium to isotropic medium just by rotating 2 layers of this material. And now let's see. I mean, these guys in twistronics, they talk about flat bands and so on. Here we have a hyperbola. It's an open curve. If you talk in topological terms, you can give a genus value here of this, like, I don't know, 1 or 0. And here, this is a closed curve. It's a circle. It has another topological value. It's like a donut. So if it goes from here to here, maybe there is a topological transition from an open curve to a closed curve. And the transition might happen as an angle in between. And we saw that at 54 degrees, there is also isofrequency curve that is not hyperbola, is not a closed curve, it's flat bands, isofrequency bands. And because they are flat, like this, you have all Ks here, like in a hyperbolic medium, all Ks coming from the center here, you have all Ks. But the pointing vector, which is normal to the curves, it's all pointing in the same direction. Meaning that you have a natural waveguide with all Ks propagating in one single direction. And this is what it's called canalization regime. It's a natural process when you twist two layers that in this case are in plane hyperbolic. So it was really nice to see. And we can make an analogy to twistronics, to twist optics. The physics is completely different, okay? It's just here, it's Maxwell equations, and it's electromagnetic coupling between the layers. This electromagnetic coupling is kind of tricky, because these are biaxial systems, and in reality, I mean, the analytical, if you go to the analytics and you go to really to the technical thing of the theory, it's kind of complicated. Even Maxwell equations can be very, very complicated, actually. But you have this transition, okay. Then we study a little bit these waves. And if you try to study let's say, the geometrical spreading, I showed you before that cylindrical wave decays like 1 over the square root of r. A plane wave, 1 divided by r, or x. What happened with these canalized waves? And then we did the fitting and so on. I saw that it's 1 divided by 1. So f, this exponent here, is 0. Meaning that there is no geometrical spreading in these waves. Okay? This is also called maybe diffractionless wave. So it's not spreading energy in any other direction because it's only one direction. Okay? So this was published at the same time, more or less, in 4 papers. Some were published in Nature, and then they have many more citations that are paper in nanoletters. But it's the same stuff, okay? And the nanoletters came 1 day after the Nature paper. Okay, so, well, this had some prize. It was nice, because it was really, really called attention in the community and so on. And now we are doing we are copying the guys in twistronics. So now, instead of 2 layers, 3 layers. And now we rotate 3 layers, okay? And Aitana had a poster. When we had 3 layers, we can disassemble it, assemble again with different angles. We saw that we can have canalization in the direction you want. You can choose the critical angle you want, and then you can canalize direction. You can make engineering of polaritons really nice way. Okay, I think with this I finished. Thank you for your attention.
Thank you, Pablo. Great tutorial on polariton physics. We have time for a few questions.
Yeah, thank you for interesting talk. Is there any connection between directionality of propagation and lifetime?
And lifetime. Yes. So in the hyperbolic medium, you can study the propagation along one direction or other directions, right? In reality, it's hyperbolic because the permittivity is changing with the in-plane direction. It's not only changing the real part, it's also changing the imaginary part. Not very much, but it's also changing. So the lifetime, and this we never actually measured this properly, okay? But the lifetime, we measure always in the direction where we have the main propagation. But if we will measure in different directions, we will see that it will change with direction. But it's difficult to measure because the wavefronts are tilted. And I want to see, I mean, we measure the lifetime by looking at the decay of the wavefronts, and then you only have like 2 because it's propagating in the direction, and then it's like, so you have to make the line profile there, and you only have like 1 fringe or 2 fringes. It's kind of complicated, but there are other techniques to measure it, but we didn't do it.
Would it be possible to do in the case of canalization?
Yes. In the canalization regime, the thing is that in the canalization regime, you can see fringes as well.
Yeah, much more. Yeah.
Because there is 1 K that dominates. The K that is, you have the 2 flat things, and then you have 1 K here, this one, that dominates 2 these ones, because they are large Ks, small wavelength, they decay faster. And then, in reality, if you make there a line profile and you study the propagation of this thing and lifetime, it's going to be more related to the K that is perpendicular than to all the Ks together. But it's you can see you have many fringes because you don't have geometrical spreading of the energy. It's a low-loss material, so we saw fringes very long in the distance. I mean, it's kind of cool.
More questions? I have a question. I'm curious, how difficult is the sample preparation when you have these nano antennas, gold nano antennas within the...
Yeah, it was the key point. These experiments, they took, I mean, this is for the PhD students, it was a 3 years project. So we started making the twisted thing, and we wanted an antenna, a resonant antenna, And we study if we put it on the top, if we put it in the middle, or if we put it down. It could work more or less in everything, in every place, but we wanted to put it on the top. But by doing lithography and spinning around the resist, the flakes were like flying away. So then we have to somehow be careful to glue the layers or try to be gentle with the layers and making the lithography. And this took a lot of time. These nanotechnological processes, they take so long. I mean, it's just the reward is not so that big for making a contact or something like that. And it's really sometimes the thing that takes longer in a PhD sometimes. But in the end, when you make it and you have the good antenna, you can see beautiful stuff. After 3 years or 2 years making the samples, when we saw this canalization, we were super happy. And 1 month or 2 months later, somebody told us, we have the paper already submitted tonight. And then, I need to write it in 2 weeks. I mean, come on.
How stable are these samples? If you can
very, very stable. MO3 is very stable. Okay. Yeah. With water, this doesn't like gremlins. Doesn't like water much.
How much power do you use in these measurements?
The power is not very high. You can see we don't have a power meter in this NOM, but with attenuators, maybe you really need to attenuate the QCL. I mean, it's with very little. These are measured with the QCL. We have the Meerkat laser with 4 chips, and this is measured at 11 microns or so. And these are powerful lines, but we have them really attenuated. I mean, with very, very small power, you can visualize this very well. Yes, it's very easy. From the SNOM point of view, if you have the right sample, it's a very easy experiment.
What kind of software do you use for processing? I mean, images, is it something written?
Nothing.
Gwydion, or just?
Gwydion a little bit, but not to, I don't subtract background fields and so on. I learned from Rainer when I was with him at postdoc. He said, no. The images cannot be manipulated, right, Rainer? Now you are subtracting backgrounds and stuff, I saw. But in the beginning, you say, no. This can be an artifact and this, blah, blah, blah. And I try not to, if I have an image that has a background, I try to reduce the tapping amplitude, the power, or whatever, to have free of background. And one hint that I do to do that is when I have a near field, clear near field, I try to get the maximum of the near field, increasing the power and other parameters, until you get some constant value in the phase. The phase is noisy if you don't have background. It's completely noisy. Imagine that you go to O3, okay? O3 is completely noisy, and you have a nice background, a nice near field. Then I increase the power to have more signal, until the phase is starting to get a constant phase.
Very good.
It's a very sensitive thing to know when you are taking background. And then you are in the optimum condition of power and signal-to-noise ratio. This is my experience. And there are other things, but you are...
Thanks for sharing this with us.
Thank you, no problem.
Okay, let's thank Pablo again.
Okay.